So our next speaker is Alexia Nix, who will talk about Wilson loops and spherical branes.
Thank you very much. And special thanks to the organizers for giving me the opportunity to talk about Wilson loops and spherical branes today. So this is based on work that we recently put out together with Davide Stesiano, Peter Bomas, Frederic Götason, and Valentina Puletti. And let me jump right in by giving a quick introduction and motivation. So in the late 90s, people already started extending the ADS-CFT correspondence to a non-conformal setting. This was done in various references, some of which I've listed here. But I want to focus on the first one, where these authors actually studied the correspondence between maximally supersymmetric Yang-Mills theory in d dimensions and flat space, and their gravity duals that are realized by the back-corrected geometry of flat dp branes. Here, p is equal to d minus 1, and for d different than 4, these backgrounds are non-conformal. Now, this idea was extended to the case of a curved spacetime, specifically by placing the maximally supersymmetric Yang-Mills theory on a d-dimensional sphere. Then, these authors of this paper realized that their holographic dual is actually given by the back-corrected geometry of a stack of spherical dp branes in type 2 supergravity. Now, by placing the theory on a sphere, this actually has a lot of benefits because it introduces an infrared cutoff in the non-conformal theory, so we have regular geometries. And moreover, one can use the tools of supersymmetric localization in order to make exact computations of observables in the dual field theory sites. So the study of these non-conformal backgrounds, so of non-conformal holography in these curved spacetimes, was actually initiated in this work by matching the 1/2 BPS Wilson loop VEV, vacuum excitation value, in the strong coupling limit and matching it with its holographic counterpart in the dual gravity theories. Now, the goal of this work is to go a step further and look at the subleading term in the strong coupling expansion and match this, at least hopefully match this, in these various backgrounds with the dual gravity side. And so, of course, the goal is to enhance our understanding of non-conformal holography. Now, let me just start by giving you the matrix model. So we have maximal and supersymmetric Yang-Mills on a d-dimensional sphere. We can use supersymmetric localization, which various people have already talked about today, so I won't go into too many details. But this is essentially what you end up with. This is the partition function. What I do want to mention is that this contribution from the instantons, since we are working in the large n limit, these will be exponentially suppressed, so we can safely ignore this. And then by just rewriting this expression in terms of an effective action, we can look at the planar limit. We see that this expression is dominated by its saddle points of the effective action, and then we find that the saddle point equations for each dimension d are given by this equation right here. Now, lambda is just the dimensionless 't Hooft coupling. D are the various dimensions of the sphere. Rho of d is the density of eigenvalues. Gd is the kernel in the various dimensions. And Bd, the boundary of the integral, are just the endpoints of the eigenvalue distribution. So in order to just give you, I just wanted to recap the kernels right here. There's also a general equation, but this is quite a large equation, so I think visually this is a little bit nicer. Now you also see that in some dimensions we have to do some kind of expansion around small epsilon. I won't go into too many details, but I just wanted to show the d equals 7 dimensions, since this is the one I will be talking about in a bit more detail. And the kernel is given by this expression right here. So since I will be talking about Wilson loops, let me just give you the definition, which was also already done yesterday, so I won't go again into too many details. But by using this expression right here, and by setting this unit norm vector n0 equal to 1, we can get the Wilson loop VEV in the large n limit through supersymmetric localization. And then what we end up with is just this expression right here, which was the famous result by Pestun in 2007. And so all we need to know, essentially, we have to solve the matrix model, so all we need to know is this density of eigenvalues. So, okay, this was already done in this paper from 2019 at the leading order in the strong coupling expansion. And it was found that for the various dimensions D, you can find that the VEV of the Wilson loop in this large coupling constant limit is given by this confluent hypergeometric function. Now, the nice thing is that in D equals 3 and D equals 4, this gives the exact answer of the VEV of the Wilson loop in the planar limit. And it also, of course, the D equals 4 case, this is the conformal case. So it also reproduces the known result, the famous result by Eriksson, Simonov, and Zarembo in 2000. Now, in all other dimensions, it also provides the leading order result, which just goes like an exponential to the power of 2 pi times the endpoints of the eigenvalue distribution. And now the surprising thing is actually, since here, notice that we only use the leading order piece of the density of eigenvalues, but the surprising thing is that we can actually get also the next to leading order scaling for all the dimensions with n and lambda of the VEV. So, and this is just given by this expression here. So what we're looking for is the prefactor of the exponential. So the next goal is to, of course, get an exact answer for all dimensions D. So we have to fix the numerical prefactor. Now, we did this in D equals 7. So by solving the matrix model that I showed you earlier, we actually got through numerical methods that the prefactor is exactly equal up to 10 digits with 12 times n. And furthermore, we were also able to fix the free energy. We found an exact expression of the free energy in the planar limit. So this is also very nice. And C here, I should just note, is just an integration constant that you can fix numerically. Again, this is perturbatively exact in the coupling constant, which is quite nice. Now let's go to the gravity dual. So on the string theory dual of this Wilson loop VEV is just given by the partition function of a fundamental string. The string, of course, satisfies the correct boundary conditions. And if we expand this, this is given by the leading order piece. If we look at the Wilson loop VEV expansion also, this is the leading order piece, so the exponential that we also saw before behavior, and then the one loop partition function. Now the goal of this work is to evaluate this for various dimensions D. The log of this one loop partition function is given by the effective action which is given by this expression right here, which contains the dependence on the quadratic fermionic. These are the D and bosonic operators that are acting on the fluctuations around the classical string configuration. And the Fradkin-Seidelin action, which is given by this expression, where phi 0 is the pullback of the delta into the world sheet, R is just the Ricci scalar, K the extrinsic curvature. Now you can easily see that for conformal backgrounds, when phi 0 is just a constant, this can just be taken out, and this just is the Euler characteristic of the world sheet of the string. But as I will show you later, is that in our cases, phi 0 is non-trivial. It's actually, it depends on the world sheet parameters. So then it will be a bit more difficult to get the exact contribution. So instead of giving you the complicated 10D geometries, I just want to give you an intuitive picture of how these geometries look like. So in the deep infrared, you actually get back RP plus 2. And if you go to the UV, you get back the near horizon limit of the flat DP Branes solutions. Now let's go to the classical part. So if we can actually express the induced worldsheet metric in conformal coordinates such that we can write it in this way. Now, rho of sigma is a smooth function defined on the worldsheet, and of course depends on the solution that we study for each case. But I do want to mention that this is a complicated metric on a disk. This disk, the boundary of the disk, is sitting on the equator of the dual as the sphere, which is sitting on the boundary of the 10D geometry. Now, using the fact that the classical string action is just given by the regularized area of the worldsheet plus the pullback of the delta onto the worldsheet, and notice the I, we're using an I because we have Euclidean branes. One can verify that indeed the leading order contribution of the Wilson loop VEV indeed matches on both sides. And this was, of course, already done in this paper, but we were also able to verify it through a different way of regularizing the area. Now, in order to get the one-loop correction, let's start by expanding the string action around this classical string configuration that I told you about to quadratic order. Then we get this action right here, where K, R, and D are the quadratic operators. These have this form. Sigma i's are just the Pauli matrices. And the nice thing that we were able to observe for the various cases is that the bosonic operators are actually given in all the cases by these equations. And this is the multiplicity in each case. And the fermionic operators, well, the functions in the fermionic operator also satisfy this equation in all cases. This is also quite cool. So now, okay, I already told you we're working, the field theory side is non-conformal, so the gravity dual is given by a non-trivial dilaton, which is not constant. So let me quickly talk about the consequences of this. Now, so in both, so what we need is the Fredkin-Zeitlin action and the effective action. These both will suffer from some divergences. In particular, the effective action has some logarithmic UV divergences, which are controlled by the second Seeley-DeWitt coefficients, and is given by this equation right here. Now you can already see that phi 0, when it's not a constant, it will contribute. And notice that we take the sigma goes to infinity limit because we want to evaluate this at the center of the disk in the infrared. Moreover, the Fredkin-Zeitlin action will contribute in this way. And again, in the cases d equals 3 and d equals 7, we actually have a singular dilaton in the infrared, so this will also give rise to some divergences. Now, what usually happens is that usually when phi 0 is just a constant, at least in the infrared, you can this does not contribute to the divergences. This term will just, only the first term will contribute, the d sigma rho term. And this actually, in the infrared, evaluates exactly to the earlier characteristic of the worldsheet. In this case, one can deduce that indeed the divergences will just depend on the worldsheet topology, and one can evaluate the ratio of two different Wilson loops that have the same topology and just get rid, thank you, of the divergences. Since they will have the same dependence on the divergences, you don't need to take any special care of it. These will just cancel in a ratio, and you can get an exact result. Now, in the cases where you have a singular dilaton, this is not so simple anymore. You find a different dependence on the divergences, so you have to resort to a different method of trying to take care of these. Now, the way we did this is we introduced another regularization scheme for extracting the one-loop partition function. And in particular, the log of the one-loop partition function we found can be just written in this way. So the first term is just a number. This is the regularized part of the effective action. And the second term contains the dependence of the one-loop partition function on the scaling n and lambda. Notice that this is a correction factor that is needed and is fixed from known results from ADS backgrounds, for example. And so this expression right here is universal. It works even when phi 0 is a constant or non-trivial. So this is quite nice. So let's check if we can get an exact result for the case that we are studying. In particular, let me show you what we got for d equals 7 and d equals 3. So for the general d dimensions, we actually found that indeed this expression gives exactly the same result as the scaling that we got from the confluent hypergeometric function. So this is very nice. Now, the only remaining ingredient was to also extract this number, which we can do through the phase shift method. This is also, I should note, this number is also fixed through the phase shift method. If you use a different method, like the heat kernel, you get a different number here. And we found these expressions for the one-loop partition functions. But as you can see, if we look at the results for the next to leading order Wilson loop, we do not get exactly the same numbers. The scaling is again correct, but the numbers are not exactly the same. We do believe that this is probably due to the singular dilaton, and this has to be treated with more care. Okay, so I don't know how I'm doing on time. I feel, okay. So let me just quickly summarize what I said. So we extracted the one loop correction for the Wilson loop for the d equals 7 case up to 10 digits, and we found that it's equal to 12 times n. But what about the cases that I didn't really discuss, the d equals 2 and the d equals 6? I should note that the d equals 4 is conformal, so it's kind of trivial. The d equals 3 is also very well known and has been derived exactly. And the d equals 5 has also been derived by Friedrich and Valentina in a previous paper. So these are actually the only remaining cases for which we don't really have an expression for the one loop VEV. So the goal is to maybe explore these cases also. We also proposed another regularization, a universal regularization scheme to extract the one loop partition function, and is needed due to the singular dilaton. We match the scaling of the one loop partition function in all studied cases, but the phase shift method does not yield the correct numerical factor in the d equals 3 and d equals 7 case. So how can this be resolved? Now, what I didn't mention is that we also performed the quantum M2 Brane computation for the d equals 7 case, so we uplifted it to 11 dimensions, and we extracted the one loop partition function. We found an exact solution, but the issue was that the scaling with n did not come out correctly, and it also didn't match the result that we had with the string partition function. But what I didn't mention is that this quantum M2 Brane background has an orbifold singularity, so we believe that since we didn't take special care of this orbifold singularity, we believe that this is the reason of this small mismatch. So we hope to also further investigate this. And finally, for the d equals 2 case, I also didn't give you many details. The pullback of the dilaton does not diverge in the infrared in this case. However, the Schrödinger problem that we have to solve in order to extract the one loop partition function shows some interesting features that do not seem to be able to be solved in the usual phase shift methods. So yes, this is also quite interesting. So yes, that's all I want to say. Thank you.
Okay, there is one question there.
Yes. Yes. Yes.
With those two different with the same topology, right? So could this be the reason of this?
Well, we don't have zero modes in our cases. We believe that there is also an ambiguity because of we're using the Green-Schwarz formalism. So already the measure factor there is not well defined. So we believe that yeah, the dilaton is doing something there. Maybe some factor is pi and some numbers are coming in there. Yeah.
And so can you say more about this regularization? So is it so you said it's not it can come?
Yes. So the thing is, so in order to get this number, you can either use, for example, in these cases we used the phase shift methods, but you can of course also use the heat kernel method, but then the number that you get from here will be slightly different. So in order to get the right result, you do have to alter this number a little bit, which is a correction factor that comes together with the measure factor. This was also done by Jumbly and Zeitlin in their paper in 2020. But yes, so if you check the results, because we actually put this here in order to ensure that you get a correct result in the ADS cases. So when you use the heat kernel, this will be slightly different. It will have a dependence on LS, but the pi, it's like 1/2 pi LS. I don't remember exactly the number, but it's slightly different, yes. Thank you.
Some more questions here.
Yeah, I'm a little bit confused about the localization setup. So you're doing maximal Super-Yang mills in every dimension, and it's non-conformal, so there are choices to be made when you put it on the sphere,
Yes.
right?
Yes.
And I know that in 3 dimensions, it's a very difficult choice, and you don't land on the right answer if you're doing in localization. You don't land on the right answer. If you just want the partition function, it diverges, for instance, which is not true. So how are you getting answers in the?
Okay. So I went very quickly here. So already here you can see that we have to do some kind of extension around small epsilon. Now here we also usually do some renormalization of the bare coupling constant in order to get rid of some weird divergences or things vanishing. And yeah, this was already done by Minahan in 2015, so I don't know exactly like his way of thinking, but all the steps that he did made sure that you got an answer.
And it's in 7 dimensions. I mean, does the theory even exist? It's a
I mean,
maximally supersymmetric
Yes.
Yang mills. It exists classically, but
yeah. I don't know. Yeah.
that's
yeah.
fine. It is some sort of approximation
Yeah.
within your horizon limit of
Yeah.
D6 range, but it's not a quantum field theory by itself. So what does it mean to do localization?
I don't know. I mean, it's okay. Yeah, it's the highest dimension you can go to, but it's also kind of a nice matrix model. And yeah, since you can. Okay, the basic answer is that you can actually, you can play around with it, and maybe the way you are playing with it, you can learn new things for the other cases
fair
that
enough.
might help you. Yeah.
Thank you.
One last short question, or urgent question. Then we have to move on. Apparently not. So let's thank Alexia again.
Thank you.